So welcome back. So now this is our first question on calculabilité. Soit la fonction prédécesseur définie par près de x given 0 si x est égal à 0 et x moins 1 sinon. We should prove that it is primitive recursive. Alright, so it's primitive recursive bien. But I'll explain like what the function predecessor mean. Just like the name implies, predecessor, those that come before. Okay, so it's been defined as the pred of x, that's what we are trying to call the function pred of x, is 0 if x is equal to 0, and it is x minus 1 if x is not equal to 0. That is if x is different to 0. Okay, so to prove that it is PR, remember we said in the first video, it was the first, I think it was the first or the second video, where it said to prove that a function is recursive, we use, okay, I think I'll do the rappel here. Here in this case, if you look at it, we can use the règle de récursion. That's to say that if I have f de x0, if you can remember this definition, we'll be having g of x, or if I have x y plus 1, we'll have h, remember from règle de récursion, h of x1 of x, because we are having just x here, f of xy and y. Okay, so this is what we say regular recursion is. Then we did a cas particulier. This was one of the cas particulier. Then we did a cas particulier where we said, what if x is equal to 0? What do we do? So in the case when x is equal to 0, this is the case when x is equal to 1. Now if x is equal to 0, it will be f de 0 equal to constant. Remember, that's what we said, to be equal to a constant. And because we don't have x, we'll be left with y plus 1, and so it will just be h of f of y and y. Yeah, so you can also put this in your record book if you've forgotten. So looking at this, we'll be able to know which of these we can use. If you look at it, you can see that we can use the second one, because in this case x is equal to 0. Okay, so since x is equal to 0, we'll be using the second formula. So let's solve using the second formula. But in this case, our f is près de x. That's the name of our function. So replace this with près de x. But in this case, since x is equal to 0, it will be près de 0 because of this. So we are going to get a constant. They said if x is equal to 0, then 0. You can see that it's almost like algorithm. So if x is equal to 0, then 0. So since près de 0 and x is equal to 0, so we are getting 0, which has verified this condition because 0 is a constant. So it's a constant. And remember when we said that all constants by convention, they are already primitive recursive and they are of arity 0. It's one of the remarks that we made in the previous video, one of the previous videos. And so we write that arity 0. And so it is primitive recursive. The second, this is the first part. Secondly, it will be près de y plus 1, because we are using this when x is equal to 0. This is the formula, this is the method we use. Okay, so we are doing près de y plus 1. So we have près de y plus 1. And so if it's près de y plus 1, it means we are going to have something like this. Près, that is looking at this, but in this case our f is près, like I said. Près de y and y. Now, yes, So if I pose my y plus 1 to be a big X, for example, if I pose my y plus 1 to be a big X, so that I can apply, because they said when X is different from 0, so that is the second case, which is y plus 1 where we are, then we apply this rule of x minus 1. So it will be y plus 1, which is going to be my big X. In this case, we're just posing it. So it will be y plus 1 minus 1. That's also showing that it's pred. That's also showing that it's a pred function, because you know the predecessor of y plus 1 is just like I have 2. The predecessor of 2 is 1. Predecessor of 1 is 0. So the predecessor of y plus 1 is y, because we subtract 1 from it. So that's basically the logic. So that's the logic. So here it will be y plus 1. We're looking for the pred of y plus 1, which we said is y. So it's y plus 1 minus 1, which will give us y. And after getting your answer here, you come back to your h, your function h, and you ask, where can I find y here? Y is in the second projection. Remember, we have 2, we have 1, this is 1, this is 2, so we have 2k. So that means k is equal to 2 from when we discussed projection. K is equal to 2 here because we're having 2. Now, and where can we find y? Y is found in the second projection. So our y is our I. You know the formula for a projection is p I k. K is the total number. We have 2. Okay, and then where can we find e, which is y? We find it in the second projection. So it's going to be 2, 2. So our projection is p, 2, 2. So that means we are going to replace h with the projection that we've gotten. So we're going to have p, 2, 2, because we're trying to say where are we getting our second projection is from here. So we have pred of y, y. In this case, it will tell the person looking at it that, oh, p, 2, 2, that means among these two is the second one we're actually looking for, which is the y. You understand? And so that means, you know, concluding it with the formula we used, I'll just do it here. With the formula we used, we said, we'll say, like, okay, we said f, doing rappel now, f is equal to the recursivity of g and h, if we can remember. And so f will be equal to, f in this case is pred, I'm sorry. So it will be pred will be equal to the recursivity. What is our g? This case is g, the constant here is g, so our constant is 0, which is g. So our g is 0, so we have 0, and then our h is what? P, 2, 2, P, 2, 2, and that's your final answer. So we can conclude that it's a function primitive recursive because by convention 0 is a constant and constants are already primitive recursive. So the first part is primitive recursive. The second one, we arrived at a projection, and you know projection is a base function, the third base function, and so we can conclude that the function pred is primitive recursive because the two, g and h, they are both primitive recursive from the explanation that has been given. So that's the first example. The second example is almost the same logic, but we'll see it. It's going to be the function sum. We're going to be treating the function sum. Is addition, that's addition. Is addition primitive recursive? So let's do it here. So the second example we'll be giving is soit la fonction somme définie par, using the lambda notation, So la fonction sum, this is definition of sum. We should prove that it is primitive recursive. We'll be applying the same principle, but I'll bring us back here again. To prove that it is primitive recursive, we have to use this. You see now that in this case x is equal to 1 because we have only one x, so x is equal to 1, and so we're going to use this method because here we have x. We won't use the second one anymore, but we'll be using the first method. So applying the first method here, that's this one, we're going to have, and again our function here, bring it back, our function here is plus. This is our function, so instead of using f, we'll be using our function here. So first we'll be having the sum of x0. Okay, so that will be equal to, the sum of x0 is what? X plus 0, which will give us x. And if you remember in one of our previous videos, again I mentioned that when you have, that's the example of the mirror type I gave, like looking at yourself back in the mirror, you see the same image. So that's what it is. This is x, right? And we got back x as our answer. And so this is, we said when we have this, it's called identité of x, because we're having the same projection. We have just one x, so our k is equal to 1, and our I is itself, which is 1 as well. So this is p, it's a projection, and we know a projection is a base function, so the first part is already primitive recursive. Now the secondly, x y plus 1, so we'll be adding the sum of x and y plus 1, will be adding. So the thing now is, depending on the function you're giving, you work with that function as the question requires, as the definition requires. The other one, we had to deal with predecessor, numbers that come before. In this case, we're dealing with sum, so that's why we are adding. The one we had to think of the numbers predecessor. So depending on the function you're giving, the same definition, it is sum, we add numbers, and here we are adding. So that's the whole idea. You just have to prove that it is primitive recursive. So x plus y plus 1. Now if you look at this closely, okay, before that let's do this. So we have h of, remember I said when we have in this method, because that's what we are using here, it will be h of x, f of xy, in this case is sum of xy and then y. So we apply that here. So we have x, sum of xy and y. If you remember again, the x plus y plus 1, if you look closely, it reminds you of the successor. The successor, we said its function successor is x plus 1, right? Function successor is x plus 1, and so this means s of x. Now if I have x plus y plus 1, its successor, and then it means s of x, y. Because it's s of x, that's why it is x plus 1. Now if we have s of xy, it will mean x plus y plus 1. That's function successor, which is a base function. It's in the first video, the first tutorial we did on this topic. So this will be, this will be the s, la somme de x, y, because it's the sum. If you see, this is just x, so that's why just s of x, but x and y is there's a sum included in it, so it's the sum of x plus y and then plus 1. You know, if it's so, with that we can come back to our question. So we see that this is the successor of x plus y. So you see how important it is to actually know your codes, because like most people, they say I better I just go for my TDs. In my TDs I'll get to know what you get my questions. When I go back to the city, go back to the hostel, I get to solve them. But actually, for courses like Programmation Fonctionnelle, you really have to understand your codes. When you understand your codes, all you just keep doing is playing around with the questions, because you think the logic and everything is right there in your codes. That's your lecture, and so you should try as much as possible not to miss your lectures as well. And even in this tutorial, I would advise you don't come directly to where the answers are if you're not already very good with the quiz. I advise you go back and watch the videos preceding this. I think this should be the 5th one or the 6th, I think so. But you should start from the beginning, get everything clear, and then you come so that when you get to this stage that we are in right now, you'll be able to understand it better. So let's go on. So that means in this case now, I'll write this clear. So this is s of plus x, y. And we now have to project it from our h, like we did in the previous question. And if you notice, this plus xy is right here, okay? And this is our successor. And this plus xy, which is here, we can find it right here. So all we do is the same thing, we just project it out of this place. So again, so that when someone is seeing it, the person will know that you're talking about the second projection out of these 3. In this case, k is 3 because we're having 1, 2, and 3, but we're taking the second one. So our PIK will be P2, 3. Okay, so replacing this right here, what is our h? Our h is the successor. We know it's the successor of plus xy, okay, but we need to bring what our xy is. We change it in form of projection, so it will be s of P2, 3. Yeah, and so we write this as well. So you see, everything is a step-by-step process. You can't actually get to miss a step, and if you do that, you might you might get confused. Okay, so you see, this is s of P2, 3, and that means you're trying to say we're getting the second from this projection. So that's how you get this back again. So what is our h in this case? Our h, you see, our h is this SP2, because this is still the same. Okay, so we've been able to conclude that this is a primitive recursive. Why is it a primitive recursive? First, we use the projection in the first case, which is already primitive recursive. The second part, successor, is a base function. Now we said a function is said to be primitive recursive if it's a base function. It's one of the 2 conditions. So successor is primitive recursive, fine. P2, 3, it's also projection and it's primitive recursive. And so in that case, if 1 and 2 they're primitive recursive, that means the entire function sum is also primitive recursive. So conclusion, plus is equal to rec de g h. And what is our g? Our g is P11, and our h is the successor. This is the same thing as s rond P2, 3. We also discussed this also in our previous video. So we can conclude that this function is PR. So you can write conclusion. sum a pair. So now the remark that I just remembered is, now you've seen you sum is pair, predecessor is pair. If I'm solving another question and then in between I get to see function sum somewhere somehow, I don't have to calculate it again. I'll just write sum est déjà pair. We've calculated it before. So that's what it means for that second condition, that a function that is already pair, we can also say it's primitive recursive when we're using it to solve another function, even without having to calculate it all over again. So would have loved us to do the third question, but I think we're already going to 21 minutes and that's already a lot to take in. So we'll see in the next video where I'll be treating the third question for this particular session. So see you in the next video and thank you for watching.